Hi everyone. We will talk about the Fourier transform in this video. It's an important issue in quantum mechanics, very, very important. And it is a particular case of basis transformations. And so we will see Fourier transforms as a special case of basis transformation or a change in the representation. Okay. First of all, let us remember a little bit about how we go from a discrete Hilbert space to a continuous Hilbert space. So I will refer here the two bases as time and angular frequency, but you can have any kind of variables, and you say these two distinct bases are dual to each other. Let us start from the real line. This is time t. Okay, time it belongs to real numbers. But let us discretize the line by endpoints from a starting point to a final point. These 2 points can be separated uh, no matter how much you want to do that. And the time interval or the space between points, for instance, a point time j to a point time j plus 1, here the separation is delta of t. Okay, so let us remember this is a continuum, but we at first we discretize it by a set of points. There are n points which corresponds to n minus 1 segments or intervals delta t. Okay? To construct the Hilbert space, each of these points will be represented by a ket vector in Hilbert space. Therefore, we will assign to each of the time j a vector, and this vector is in Hilbert space. It will be represented like 1 over the square root of delta t, zeros to get to the position of that point in this vector. So a 1 at the j position here, and zeros otherwise. And we'll have a vector of n lines by 1 column. This is a column vector, a ket vector in Hilbert space. Okay, that's the situation here. Notice again that points in line are not orthogonal to each other. They belong to the same line, but in Hilbert space, each point is represented by a vector. So this tj point is represented by that vector, and that vector is orthogonal to another point, to another vector representing any other point. Therefore, we construct a complete basis. So Tj Ti is equal to a Kronecker delta Ij, but divided by delta t, because we normalize these vectors by the square root of delta t. If you are dealing with a discrete Hilbert space, you don't need to renormalize the vectors, and you'll have just the Kronecker delta. But we are interested in taking the limit where delta t goes to 0, and therefore you can take greater and greater values of n, the number of points, and this way the delta t becomes smaller and smaller, and you'll have more zeros inserted here, here, and here, and the one will be placed at exactly the point tj. But as long as you go n tending to infinity, you will put more and more and more and more and more rows in this vector. So it will become very dense, full of zeros and one in a particular position here. It's just a mathematical representation. Therefore, a point in line is represented by a vector, a ket state, in a Hilbert space. And this ket is orthogonal to any other. Therefore, I can say, we can say that any point is orthogonal to any other point in the line, because you can represent it by a vector in Hilbert space. Okay? And a simple representation is this form of the vector. It is normalized by the square root of delta t. Okay? If it forms a complete basis, we have a summation from 1 to the dimensionality of the space, which we will make n going to infinity. The delta t, tj, the exterior or the tensor product of the bra, and you get the identity here. Notice that since we are renormalizing this thing by the square root of delta t, I need to multiply it by delta t. And if you go to delta t tend to 0, which means n going to infinity, this summation, this sum, will tend to an integral. The sum where the interval of points going to 0 is the definition of an integration. Therefore, I have a basis in the variable t, a basis of time, say. It can be position or any other variable you are interested in. Now, I have this form, time, t, a set of vectors in the continuum will satisfy the Hilbert space properties, which means time t prime projected to the time t, okay, will produce a Dirac Delta, t prime minus t, okay? The limit of delta ij, the Kronecker delta over delta t, when the delta t goes to 0 and I eventually goes to j, this goes to infinity or it goes to 0 otherwise. This is the definition of the delta, t prime minus t. T prime here corresponds to, in the discrete sense, to the t subindex I and t subindex j. Okay, that's the question. We define the Dirac delta here. It doesn't matter the order here because the Dirac delta is a even function. You can change the sign, the internal sign in the argument, and you get the same sign of the function. It is an even function. Okay, the Dirac delta is defined as even by substitution. So you have a delta of x is equal to delta of minus x. Okay, that's no problem there. So the basis must satisfy completeness. So if I integrate over del dt the tensor product or the exterior product, we'll get the identity. So this defines the basis of the variable t or time eventually. I can do the same thing in another basis. Let us call this omega. I can discretize the line. Omega initially belongs to the real numbers. I will have omega 1 to omega n. And same things we attribute to every point in the line a ket vector. So this omega 1 here will be represented in a Hilbert space by a ket omega 1 and has a complete basis. I don't know in principle how to represent the terms, the components of the vector in the time basis, for instance, at least for now. But I can assure that if I have another complete basis in the limit where the delta omega goes to 0, same thing as we do for the t, omega prime projected to omega will produce a Dirac delta. This is completeness of the basis, the orthogonality of the basis. Sorry, and it will certainly satisfy the relation of completeness or closure. So we'll get here the identity if we integrate over all the possible omega values in the real line. Okay, so I have one, the time basis, and the frequency basis. There are two distinct bases. Okay, now both bases must satisfy the completeness and orthogonality or orthonormality relations in Hilbert space. So suppose I have an object, okay, psi, a vector in Hilbert space. The vector psi, the ket, is a ket vector in Hilbert space. And I want to know a particular component of psi in the basis of time t. Okay, if I have a discrete basis, I'll project it to one of the vectors of the basis, and I could, for instance, represent that as a component psi of tj. But as long as the variable time becomes a continuous variable, the index here becomes a continuum, and for continuum we represent it as an argument, and the components of that vector become functions. Okay, components are in fact functions. So C of the time t is just the projection of the object psi, the vector, the cat in Hilbert space, in the basis vector t, which is representing time, for instance, or we could represent position in another problems. Notice that if I go to a discrete world, I would have psi equals to a set of numbers, psi 1, 2, and so on. And the psi j would correspond, if I represent it in the time basis, the psi j here in this vector would correspond to the value of the vector, the component of the vector, in that specific point in the real line representing time. But as long as I go to a continuum, this vector becomes the dimensionality of this vector becomes larger and larger. I will have more and more entries here, and in the limit, it will become a parameter, each component indexed by a continuous variable, and this continuous variable indexing something, we call it a function. Okay? So this is what we can say it is a vector space of functions. Okay, it's a vector space of functions. So this is what we have. C, the psi, the vector, the component of the vector psi of this object in the basis of t, and at the exact specific time t, which corresponds to a vector in Hilbert space, is just obtained by projection. You can project the object over that specific vector and you get the component. Okay? So a function represented in time can be interpreted as the component of a vector which is invariant in Hilbert space in some sense. Okay, the object is a vector, it's invariant in Hilbert space, but I'm using a specific basis in the Hilbert space, and this specific basis I'll call time, and the projection of that object along the direction of this time t produces the component c of t, which is a function. Okay. Well, I can do the same. I'll call the component psi tilde of omega. I can do the same if I pick this object and project over the basis of omega. Okay. The two bases are distinct. So these numbers are the components of the vector in the time t, this basis. And psi tilde of omega corresponds to the components of the same object, the same in Hilbert space, invariant object, but projected in the basis of omega. The, say, angular frequency or momentum, if you're dealing with quantum mechanics, this can be time and angular frequency, or it can be position and momentum, or wave vector, for instance. Okay. Well, now I want to perform the connection between this object and this, which means I want to produce a basis transformation, a change in the representation. So what I need to do, okay, I'll do that. I'll introduce completeness, the resolution of the identity in terms of a given basis. So, for instance, consider psi of t. Okay, psi of t, I know it is the projection of the object, the cat, along this direction, but I now can insert the identity. So let me write it very carefully. Time t, identity here in the middle of the sandwich. I insert the identity here and the vector here. So the identity times the vector, it corresponds to the vector, and I have this result. But I will resolve this identity in the other basis, in the basis of omega. Therefore, I can write it as the following is equal to time t integral over d omega this is the identity. The limits of integration usually go from minus infinity to plus infinity, but if you have a limited space, the real line is limited, then it goes from some value, inferior value, to a superior, and is settled. And now this is a summation I can put in front of everything because the product and the sum can be interchanged here. So I'll write it as the integral of d omega, say from minus infinity to infinity for now, and time t projected to omega projected to psi, and this is just what we called psi tilde of omega. Okay, and this is the coefficient, or these are the coefficients because there are infinite number of them. The coefs of basis transformations. Okay, these are the coefficients of the transformation. These coefficients are the ones I must determine now. Okay, the same I can do for the inverse transformation. Suppose you have psi tilde of omega. This corresponds to omega projected to psi projected to the direction omega. I can insert here the identity, but now resolve it in the basis of time, and therefore I can, jumping from the intermediary steps, an integral over dt from minus infinity to infinity omega projected to time here, psi here. This is what we call psi of t, and these are the coefficients of basis transformation. Okay, notice this is the complex conjugate of the other transformation. So allow me to rewrite two equations here together. I hope I'm not going too fast in these demonstrations, but you'll have psi of t is equal to an integral over d omega from minus infinity to infinity time t projected with omega this way, psi tilde of omega. And if I go the other way, psi tilde of omega is equal to the integral, say the limit goes from minus infinity to infinity, dt omega projected with time t. Or, as I said previously, it can be position and momentum, then momentum and position. And here we have psi t. This is just a coordinate transformation, a basis changing, a basis transformation, it's better said that way. T projected over omega is equal to the complex conjugate of omega projected to time t. That's what we have in Hilbert space because of the definition of the inner product or the dot product. It's well defined. The modulus of that thing is positive and all that. Okay. We know from the theory of basis transformations that a basis transformation is a unitary operation. Therefore, these coefficients, if you go to a discrete space and frequency, or perhaps a discrete Hilbert space, better said that way, will produce a matrix, and that matrix will be a unitary matrix. A matrix going from omega to t, and the other, these matrices go from t to omega, and that's the transformation, okay? These are said to be dual spaces, okay, or reciprocal spaces, dual spaces. T, I can go to omega and back. This is a two-way transformation. You can go and you can go back. Okay. Well, now we need to know what are these transformation coefficients. That's the problem here now. But I have basis properties which will allow me to obtain these coefficients. Remember one thing, a delta, a Dirac delta represented in the time domain, say, is in an integral representation defined as 1 over 2 pi, the integral from minus infinity to infinity of an exponential. Exponential which you can assign any of these signs, plus or minus, it doesn't matter. Pi, the imaginary unit, a variable omega, t prime minus t integrated over the omega. Of course, define for any variable, just integrate the other one. It could be time and frequency, it could be position and momentum, it could be momentum and position, or frequency, angular frequency and time, doesn't matter. So again, you can choose one of the signs. It doesn't matter what sign you choose. If you integrate that way, you get a Dirac delta. It is easy to understand because suppose the time t prime is distinct from time t. This gives you a finite number. So you'll integrate over a multitude of frequencies, as a matter of fact, from minus infinity to infinity in frequencies. And the integrand is oscillatory, and the oscillations are ensured by the fact that t prime minus t is a non-vanishing number if t prime is distinct from t. Okay, and this way you add up a lot of oscillatory functions, and the result, a probable result, is zero, because you have a function oscillating with a positive value and another one in another frequency which goes uh, to a negative value. Then you have a lot of oscillations here. You add up every term, and you get zero that way. Okay, you get zero because fast oscillations cancel each other. But when t prime is exactly equal to t, this exponential, no matter what frequency you put in here, will go to, the argument here will go to zero, because t prime is equal to t. And in this case, this exponential will be e to the zero. E to the zero will give you 1, will give you the unity. And you integrate unity from minus infinity to infinity, and this gives you an infinitely large number, an infinite. It diverges. And this is exactly what defines a delta. A Dirac delta is a function which goes to zero if t prime is distinct from t, and goes to infinity if t prime is equal to t. Same here, but for frequency. And you can say x prime x, k prime k for space variables. It doesn't matter. I'm saying time and angular frequency here, but you can choose any mathematical variable you want. There are space t and a dual space omega, a space x and a dual space momentum p, for instance, in an appropriate system of unities, of physical units. Okay, so or you can use position and wave number, x and k. Okay, well, this is definition of a Dirac delta. You have this thing here. Now remember, t prime projected over t is equal to the Dirac delta, t prime minus t. We know that t prime projected over t gives a Dirac delta, because we are talking about basis vectors which satisfy all the properties of a Hilbert space. And this I can write as 1 over 2 pi, that integral which we discussed. I don't know what sign to choose yet, so I'll put any of the signs, prime minus t integrated over the omega. As a matter of fact, the sign convention is distinct in engineering, in the many applications, from the physics convention, and it doesn't really matter. We'll choose the convention of interest in quantum mechanics, but that convention, just remember, you're talking about the unitary transformation, so it will just impact the other, the inverse transformation, or the inverse transform, say, in the case of Fourier transformations. Well, now I will insert here a unity. Here, a unity. This is the delta, but the unity I will resolve in terms of the other basis, the frequency basis. Therefore, this unity here can be written as d omega, omega, omega. I insert it here, and I can change the integral with the products. So I can write this as d omega from minus infinity to infinity here, t prime projected with omega, omega projected with time. I don't remember if I said it previously, but we always represent the scalar product of two vectors, phi and psi, for instance, any two vectors. This way, because we are really doing this, a scalar product or an inner product. But the Dirac convention is, if you have a scalar product, you don't need to write a bar and another bar. You can eliminate the dot, and this is the convention. When you see this, you must understand it is a column vector, is a row vector, and the product is a scalar. Okay. Well, it's done. I have it here. T prime projected to omega, omega projected to t. It is integrated over omega. I can compare this is this, and I can compare this expression with the representation of a Dirac delta. Okay, that's what we need to do. So notice that I can write the equation defining the delta as follows. 1 over 2 pi integration of, in the limits of minus infinity to infinity. I will remember that 1 over 2 pi is equal to 1 over 2 pi square root of that, and I can square again. So I take the square root and I exponentiate to the power of 2, or it's the square root of 2 pi to the 2. So I can rewrite it here the following way. That equation, I can write it as the integral from minus infinity to infinity exponential plus or minus I omega t prime divided by the square root of 2 pi, and exponential, if this is plus, with the minus you get a minus. If this is minus, with the minus you get a plus. I omega t divided by square root of 2 pi. I am normalizing the exponentials, okay? But the product gives me that 2 pi here and integrated over the omega. Now I have the integration over the omega. It doesn't matter if you put the integration variable here or in the end of the equation. It's understood that you integrate over omega here, as well as here you integrate over omega. Okay. Now we can compare. T prime appears here, so this thing must correspond to that projection, and this thing must appears time here corresponds to that projection. Okay, and you have your Fourier transform. Okay. Well, now it's a matter of convention. You can choose a plus, and this is a minus. You can choose a minus. This is a plus. It must be fully, 100% compromise with your 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 choice. You need to follow your choice. If you choose a plus here, you need to choose a minus here. This thing, if you put time t prime equals to time t, this thing is the complex conjugate of that one, and you need to have well-defined things. You cannot choose plus here and plus here. Okay. So we have this t prime projected to omega is equal to 1 over square root of 2 pi exponential of r plus or minus I omega t prime e to the plus I omega t prime, and the other 1 over square root of 2 pi minus or plus I omega t. Okay. Now we can choose our convention. C of t is equal to the integration over minus infinity to infinity integration over d omega t projected to omega c tilde of omega, and in quantum mechanics we always choose this to be e to the minus e omega t. So this projection here, I must choose the minus convention. So e to the minus I omega t prime here over 2 pi, and this gives me only one option, which is the plus sign, which will give the inverse transformation. Okay, and of course it is already normalized by the square root of 2 pi. In some sense, any transformation, any transform is a basis transformation. You can find another transformations between variables, and that is only a matter of finding an integral representation of a Dirac delta. The Fourier transform corresponds to a basis transformation in which you choose to represent the Dirac delta by the superposition of harmonic functions, of exponential functions of this form, okay? And of course, psi tilde of omega corresponds to the inverse. You integrate over time, you'll have omega here, time here, c of time here. So notice that t projected to omega corresponds to that, and the inverse transformation corresponds to the complex conjugate number. Okay, so this is a Fourier transform. Fourier transforms are basis transformations in Hilbert space. Okay, our Fourier transformations will be defined this way: C of t, psi of t is equal to 1 over the square root of 2 pi, an integral from minus infinity to infinity psi tilde of omega, which correspond to the spectrum of the function e to the minus I omega t integrated over all the frequencies. And the psi of omega tilde, the inverse transform, which corresponds to, now here you go from omega to t, and the other goes to t to omega, goes from t to omega. Better said that way. It's psi of t exponential plus I omega t, properly normalized. Okay, just you work very well this way. Usually in quantum mechanics, because we usually deal with uniform plane waves as a way to represent space-time functions, the part involving time and position and momentum, if you have a function of x, say one space dimension, is defined as 1 over the square root of 2 pi, the integration from minus infinity to infinity tilde of k subindex x, because you can have a y and z, so you have k x, ky, and kz, and the integrals are in a volume, say. You have this plus I kx multiply or times x dkx. Okay, and if you need to find the inverse, same thing here, but you integrate over space from minus infinity to infinity, and you just change the sign here and change the variable of integration. So that's convention. I will try to summarize a little bit what we found here about Fourier transforms. Well, Fourier transforms. Fourier transforms just correspond to basis transformation in Hilbert space. That was a Fourier. That is what a Fourier transform represents. Just a basis transformation. And you can go from, in general, okay, in general, you can have a variable alpha and a variable, say, beta. Fourier transform goes from one domain to the other one. Okay, that's it. Or from the real space to the reciprocal space. In many places they call it that way. You can integrate over the beta to find the components alpha, and the other way you integrate over alpha to find the components in the domain beta. And alpha and beta are said to be dual or reciprocal variables. Okay, and the projection of alpha over beta corresponds to the I to the plus or minus, depending on the convention, alpha multiplying beta divided by the square root of 2 pi. And of course, the inverse transformation, you need to take the complex conjugate of that. Therefore, beta over alpha gives a minus plus I alpha beta divided by the square root of 2 pi. Okay, that's it. That's it for Fourier transforms. Fourier transforms correspond to basis transformations in Hilbert space. And as I said previously, you can find another forms of projections in another representations of the Dirac Delta, and you find another transformations, generalizations of Fourier transforms or another transforms. There are a lot of transforms, Hilbert transforms, Fourier Bessel transforms, and so on. There are a lot of transformations which just represent a basis transformation. This way, an object psi, a function psi, which is represented by a vector in Hilbert space, this object is interpreted to be invariant, independent of the representation. But the components are dependent on the basis you are using. And the basis transformations just show you how to represent this object in the other basis if you know the components in a given basis. You know the components in the basis of beta. You can find the components in the basis of alpha. If you know the components in the basis of alpha, you can find the components in the basis of beta. And that's all you can do about basis transformations. I emphasize that point. Fourier transforms corresponds just to basis transformations in a Hilbert space, in a vector space of complex vectors which are objects invariant in the Hilbert space. When you find a Fourier transformation, you are just making finding the components in another representation. If you know one, you can find the other representation if you know how to connect the two bases. Okay, that's important thing here. Last and important, there are a lot of properties of Fourier transforms. Okay, I'm not going into the details, but for instance, if you have psi of t defined this way, 1 over square root of 2 pi from minus infinity to infinity, function represented in omega domain, and this is defined as minus the exponential of minus e I omega t integrated over d omega. If you take the time derivative of that function, I will represent as a partial derivative because this function in the future will be a function of space and time. So if you have a time derivative in the other domain, you can see it's not the proof. The proof is a little bit tricky. You use partial integrations and you transform this, but it's easy to see here that if you take the time derivative, you can take time derivative here, you derive this expression, the only dependence on time is here, and you get the coefficient minus I omega. Therefore, a time derivative in the time domain corresponds to a minus I omega multiplying the Fourier transformed function or the components of the function in the omega domain. Also, if you have a derivative here in the omega domain, it corresponds to a imaginary multiplying time psi of time. That's a dual way. You can go from time derivatives to multiplications in the frequency domain, and you can go from frequency derivatives to time multiplications or in time domain, or that's a general property. There are other properties, very important properties, but I will focus on another important, very important result from complex algebra, and in particular Fourier transform, which is named the Parseval's theorem. Okay, Parseval's theorem. It's a very important result, and it can be really easily understood in terms of basis and the property that vectors in Hilbert space are invariant. So suppose you have the scalar product of two vectors, a vector psi, a vector phi, and you produce the inner product here. So you can introduce, as always, the resolution of the identity in the middle of this, let us call it a sandwich. So you can now represent the identity. You can resolve the identity in any basis in Hilbert space that you want. And in this way, you can write it as d omega phi omega omega psi, which is equal to the identity resolved in the basis of t, or in another basis you want. Notice that this is the integral over d omega. This is the complex conjugate of the component of phi, and this is the component of psi in omega. Here you'll have integration of over time over the variable time. This is the complex conjugate of phi over time, and this is the component of psi in the time domain. And what we are saying is that the scalar product, that's what Parseval's theorem says. It says that the scalar product of two vectors in a Hilbert space is independent of the representation. It independs of the basis you choose. You can integrate over or sum over the components, multiply. This is a scalar product in the basis of omega, or in the basis of time, or in another basis do you want to use here. And the result of the scalar product is independent of the basis you choose, because these objects, when you change basis, you are just like rotating, and the scalar product is invariant under rotations. But you must know that the rotation is in a Hilbert space are represented by unitary transformations, and they are rotations, rotations in a complex vector space. That's important to say. Okay. So if you plug in here phi equals to psi, you'll find the very, very known property of Fourier transforms, which say that scalar product is independent, or the size of this vector is independent of the basis you choose. Okay, if you plug in phi equals to psi in the previous equations, you'll have the omega, the psi complex conjugate multiplied by psi, which is equal to the square of the modulus. Okay, you sum up, integrate, which is equal to integration in the time domain. Okay? This way, Parseval's theorem is just a consequence of invariance of the objects, independence of the objects with the basis you choose to represent them. You can represent them in time or in frequency or in another basis, and this is usually linked to the energy content of the function. The energy content, or the sum of all the components modulus squared, the square of the modulus, is independent of the representation. Okay. Well, another important uh, property or identity in Fourier transforms is the uncertainty principle, which plays a fundamental role in quantum mechanics. I'll not work the uncertainty principle here because I guess I talked too much already, and I'll finish this lecture here. Okay. Next steps will go more deeply to the postulates of quantum mechanics, I guess. But this is a very, I guess, introductory uh, review of the basics, the mathematical basis you need to understand quantum mechanics. Hilbert spaces and Fourier transforms. Okay? In Hilbert spaces, you have discrete Hilbert spaces, continuous Hilbert spaces, and Fourier transforms are very important uh, tools to work with quantum mechanics within the problems of quantum mechanics. Okay, I'll see next time.